Hello, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today, we have Kevin DeFord. Kevin is a Product Commercial Senior Manager at Smiths Interconnect. Joining Kevin today is Kyle Gobble. Kyle is a Product Line Manager at Smiths Interconnect. For today's agenda, we are going to focus on common contact technologies used in the connector industry and how to avoid fretting corrosion by implementing Hypertac hyperboloid contact technology for your connector designs. We are going to understand the difficulties in surviving harsh environments. We'll find out how to avoid fretting corrosion. We're going to discover the Hypertac hyperboloid contact technology for your connector designs. And at the end of today's webinar, we will have kind of an open discussion and a Q&A session. So with that introduction of the presenters and going through our agenda, I am going to pass things along to Kevin to kind of kick us off today. So Kevin, go right ahead.
Okay, thank you, Katie. Good morning, good afternoon, good evening, wherever you are, and thank you for your interest in our webinar today. So, fretting corrosion. So what is fretting corrosion? So fretting refers to the wear between two contact surfaces that have a load applied between them and are subjected to micro movements occurring tangential to the surface. So corrosion occurs between any two materials that are susceptible to chemical reactions, namely oxidation. And tribology is the science of surface interactions in materials with relative motion between them. So an integral part of electrical connectors are the contacts within them that make electrical connections between two systems. The contacts typically have a male pin or blade and a female receptacle. Most electrical contacts are plated with gold and have an electrolytic nickel plating underneath them that acts as a barrier between the substrate and the gold. The gold is inert to oxidation, but is soft in nature and prone to wear. When the contacts are subject to micromotions and the gold is worn away, the nickel is exposed, which creates non-conductive oxide layers. As the micromotion continues, these oxides accumulate in the valleys of the asperities. Sorry, I'm on the wrong slide. So the asperities shown here in the center So as the micromotion continues, these oxides accumulate in the valleys of the asperities and insulative layers in the contact are formed, increasing resistance, which inhibits the flow of electrical current, increasing the Joule heating between the contact points. As this process continues, it leads to further power loss, signal distortion, and eventually component failure. So electrical contacts are usually made from copper alloy, such as beryllium copper, phosphorons, or brass. Contact surfaces are inherently rough, and electricity only flows between contact spots called asperities, which are microscopic hills and valleys in the surface. When a force is applied, the asperities flatten out. The more force that is applied, the more contact that is made between the 2 points. When a fretting motion is induced, the noble coating, gold, is worn away and the nickel is exposed. As the fretting repeats, the oxide layer is wiped away, new oxides form, and the cycle begins again. As the process continues, the oxide particles get trapped in the depressed regions of the asperities, which build up and increase the resistance. Eventually, the accumulation of debris becomes great enough to prevent current from flowing between the electrical contacts and leads to contact failure. So what are some of the causes of fretting? So fretting can occur in any environment that is subject to vibration, shock, or temperature extremes. The motion between contact surfaces is generally small, about a few thousandths of an inch, and the frequency of the movement is dependent on the environmental conditions that exist. So vibration is the leading cause of fretting and corrosion failures. Connectors used in applications such as engine controls and power distribution units in military aircraft, drones, and helicopters excuse me, are all prone to high levels of vibration, shock, and temperature extremes. Section 514.6 of Mill Standard 810 defines the vibration profiles for military aircraft. The vibrations induced in aircraft vary depending on where the connector is used. So vibrations levels seen in the tail of an aircraft vary from those used in controls in the cockpit. Another common cause of fretting is repeated thermal cycles from cold to hot. As the contact surfaces are heated and cooled, the materials expand and contract, causing micromotions. Power cycling can also contribute. As the power is cycled on and off, the metals heat and cool. High temperatures also increase the rate at which non-noble metals oxidize, nickel, for example. So lastly, repeated mechanical shocks can also induce micromotions in electrical contacts and lead to failure. The mean time between failure may be greater in this case, but all attempts should be made to prevent any of these factors from occurring at the contact surfaces. So don't fret. There are ways to combat fretting corrosion, and we will discuss the pros and cons of each. One method is to increase contact force between surfaces. There are physical limits to how much force can be increased, and while it may improve mechanical stability, it can also reduce the mating life of the connectors. Another method that is used is applying lubricants to the contact surfaces. Lubricants are effective at reducing fretting wear and increasing contact life. They can also be effective at protecting connectors from the elements and preventing oxidation. Lubrication comes in many forms, such as grease, there are dry lubricants, and other commercially available wet lubricants that can be used. Lubricants can be messy, and they tend to attract dirt and soot and can migrate to unwanted places in an electrical system, which isn't right for every application. In some cases, you can implement hardware in the system to prevent movement between connectors. For example, 38999 connectors employ a coupling mechanism to lock the connectors in place. In PCB connectors, alignment and locking hardware can be employed, but this comes at an additional cost, and sometimes board real estate is a premium. It is important that you maintain regular maintenance and inspection program of electrical connectors to look for signs of wear, which is an indication that corrosion has begun. This could appear as dark spots on the electrical contacts or signs of foreign material on the connector faces or surrounding areas. Cleaning the contacts, if possible, can prolong the life, but often replacement is required. So lastly, you can design redundancy in the electrical contact system so there are fewer potential failure points. One way of doing this is to increase the number of contact points within the contact so there isn't a single point of failure. We'll dive deeper into this subject later in the presentation. So now I'm going to hand it back to Katie, who will issue a poll question.
Great. Thank you so much, Kevin. So for the audience today, we do have a polling question, and we would love it if you would participate. So that's on your screen right now. The question today is, what would be more important to you when selecting a connector for harsh environments? So first option here is corrosion resistance. Second option is high number of mating cycles. The third option is stable signal integrity. And the fourth one is all of the above. So I'm going to leave this up on the screen for about 30 seconds to give you all some time to submit your answers. We appreciate your participation. And I'll just read the question out one more time for all of you. What would be more important to you when selecting a connector for harsh environments? And if you would click on your response, that would be great. I'll leave it up there for about another 5 seconds to get any last minute responses. All right, guys, and I'm going to push us over to our results slide. We appreciate your participation in our poll today. And Kyle, I'm going to pass this over to you if you want to talk about any of our results.
Thanks, Katie. Hello, everyone. Okay, so it looks like why settle one when you can have them all, right? So no surprise there. So let's see how this applies. So environmental specifications in military systems. There are many different environmental specifications in the industry today. As Kevin mentioned, most are written directly from MIL DTL A10 or a variation of such standard. One example of this is ANSI-BETA 47 and its various dot standards you see here on the screen. Some general details of these specs will be mentioned in the following slides. However, in general, BETA 47 is the specification for commercial off-the-shelf plug-in modules intended for ground and aerospace applications. These plug-in cards can be anything from single-board computers to mission-critical sensors, all of which requiring electrical contacts. In the next few slides, we'll review the environmental requirements of vibration, shock, and temperature, and how threat and corrosion is an ever-growing concern in these environments. So vibration. Vibration is the first environmental condition that comes to mind when someone thinks harsh military environmental requirements. BETA 47 uses classes to define the level of vibration requirements for each system. So class 1, you see here, being the lowest level at 1.95 GRMS, whereas class 3 is the highest at 12 GRMS. So, however, some work has been done within the BETA 72 work group to push these limits and elevate the connectors in these systems to higher levels to about 16.5 GRMS. As these requirements continue to increase, so does the presence of threat and corrosion and the need for next generational connectors to mitigate these effects. Shock, like vibration, BETA 47 breaks mechanical shock into classes. So class 1 being the lowest level at 20 Gs, and class 2 being the highest at 40. Again, BETA 72 has done some work here. They're pushing these levels to 50 Gs and additionally to 80 Gs in the X and Y direction. Similarly to vibration, as these next generational environmental levels increase, so do the effects of threat and corrosion over the life cycle of the connector. Temperature. Temperature is often overlooked when considering threat and corrosion. The repetitive expansion and contraction of metals, which changes in temperature, can cause the micro movements on the surface of electrical contacts and eventually lead to threat and corrosion. It's important to note these are system-level temperature cycling requirements, which are used to determine resistance of exposure to alternating streams of highs and lows. Some components in these systems may reach higher temperatures. To make matters worse, system architecture continuously pushing speeds and power levels, generating more and more heat in the process. Now back to Kevin to talk about different types of contact technologies.
Thanks, Kyle. So now I'll provide an overview of some contact technology used in connectors. So here are a few examples of commercially available contacts. So on the left, is the pin and socket contact. These contacts are usually made from beryllium copper and plated with various amounts of gold and electroless nickel. The female socket can be machined or stamped, and the ends of the female are formed into a circle to make contact with the male pin, generally at 2 points. The male pin is round and makes contact at the mouth of the receptacle, which pinches the pin, making the electrical connection. This type of contact provides a low-cost alternative and is suitable for most industrial applications where you would expect less than 500 mating cycles over the life of the connector. Due to the construction, it would be susceptible to fretting corrosion in applications that are exposed to vibration, shock, or thermal cycles. Second type is the tuning fork style contact. This is similar in nature to the pin and socket. It is stamped from flat stock and formed in the shapes like you see here in the center of the screen. So this style of contact is usually comes in the form of a tape and reel, and the female is selectively plated to save on costs. The male portion is square in shape and obviously usually insert molded into commercial PCB connectors. But like the pin and socket, it provides 2 points of contact. It's prone to the same fate. It has a low mating life, generally less than 500 cycles, and is subject to fretting and generally perform poorly in harsh environments. So lastly, the bent metal contact, sometimes referred to as a shield or ground contact. This is a stamp contact that's selectively plated and can be provided in tape and reel. So these contacts are simple in design and can be mated to flat surfaces. It's a single point of contact and is generally designed into applications such as low-cost battery contacts. One fault of this type of contact is that if they become overcompressed, they are vulnerable to cold setting and permanent deformation. So this contact would definitely not be recommended for high reliability applications. So Smiths has a long reputation of designing high reliability connectors for harsh environments. The Hypertac hyperboloid contact is an advanced contact system that satisfies the performance requirements in these types of high reliability applications. So it was originally designed in the mid-1950s to address issues associated with high vibration in rail applications that experience problems with electrical intermittencies in connectors. The contact has a hyperboloid-shaped basket that is formed by wires strung at angles to the axis of the socket. So the wires are plated with electroless nickel and 50 microinches of gold. When the pin is inserted into the basket, the wires stretch around it and provide a high number of linear contact points that are redundant and give a very low resistance path between the pin and the basket. So the wires, because of this, the hyperboloid has a higher current rating than comparably sized contacts and is rated to up to 10,000 mating cycles and performs very well in environments. I'm not sure why this continues to, the slides keep changing on me. So as I was saying, it performs very well in environments where shock, vibration, and thermal extremes exist. So when designing in connectors for high reliability applications, the Hypertac contact has stood the test of time and has been qualified into the most demanding applications. Over the years, as the Hypertac contact technology was reduced in size, this reliability was recognized in other industries and was increasingly used in aircraft, military, defense, space, test, and medical applications. So now I'm going to hand it back to Kyle to talk more about our KVPX backplane connector and how it uses our flagship Hypertac contact.
Thanks, Kevin. Let's jump over here to the correct slide. Not sure why I was jumping around on you there. So KVPX, as Kevin mentioned, the KVPX connectors are equipped with a Hypertac space qualified 0.4 millimeter hyperboloid sockets, as Kevin mentioned, and provide immunities to shock and vibration and fretting, numerous linear paths of contact, and low insertion forces, high mating cycles, and a self-wiping cleaning action that results in consistently better integrity in extreme environments. The KVPX interconnect system meets all of the high-speed electrical requirements of VITA-46 and 48, while vastly increasing the mechanical reliability and physical ruggedness of unmated connectors and modules. Its modular design supports custom designs in 3U and 6U configurations with differential modules tested at the speeds up to 16 gigabits per second, as well as single-ended modules with analog and RF signals up to 8 gigahertz, and power modules, which are also available to the designers. So a little bit more about what those building blocks are. These daughter card connectors are KX1 part numbers, which you see on the top left image, can be used as building blocks combining various full width and half width modules with utility, again, single-ended and differential wafer types to meet any system I/O requirements. The complementary backplane connectors you see on the bottom left are essentially universal in nature. They're just sockets, a hyperboloid socket. They're operated, again, both half and full widths, which are 72 socket and 144 socket configurations to match those full and half width KX1s on the daughter cards. So in today's discussion, we concentrate on vibration, shock, and temperature requirements, which we'll compare a little bit more in the following slides again. However, shown as such, including some of the other general specifications of the KVPX connector system for your reference. Some key benefits include the greater than 4,000 mating cycle life, extraction forces of 1.9 ounces per contact. If you add that up, it essentially equals to 274 ounces, or just 17 pounds for 144 contacts in our full width modules. Also, the industry accepted 50 microinches of gold is key to ensure our contacts endure in these harshest environments. So comparing the specifications to the KVPX, we combined essentially the environmental requirements from VITA-47 and that of a next generation requirements side by side. It's easy to see how the KVPX connector outperforms current environmental industry standards. Our KVPX, for vibration, our KVPX meets VITA-47 class 3 levels and exceeds the tester duration by 30 minutes in each direction. However, recent testing has been completed successfully up to 15 GRMS at 10 to 2000 hertz as they move towards qualifying the next generational connector requirements we see here. For shock, as you can see, our current specification exceeds the current VITA-47 maximum requirements, which is class 2 in this case. The 50 Gs instead of 40 Gs at 11 microseconds with the sinusoidal response spectrum. However, again, we've done some recent testing to show up to 100 Gs at 6 microseconds with a sawtooth response curve, which postures us for next generational system requirements. For temperature, finally, the KVPX connector system is well suited to meet all ranges of the current system level temperature requirements, while current qualification testing is not far from next-gen systems. So with that, thank you for taking the time to attend today's webinar. Please join us again in our next webinar, where we will go into more detail on KVPX. For more information on how to sign up, please follow us on LinkedIn or go to our website. Now I'll hand it back to Katie for any questions.
All right, great. Thank you, gentlemen, so much. So Kevin and Kyle, we appreciate the great presentation. We are going to move into taking some questions from our attendees at this time. All right, gentlemen, so I'm going to just grab our first question here today. And to me, Kyle, maybe you can take this one here. What is the smallest pitch a hyperboloid can reach?
Yeah, I can take that one. So pretty simple. Currently, our smallest pitch contact is 0.3 millimeters, but we have contacts that go all the way up to 27 millimeters.
All right, great. Thank you so much for that answer. All right, gentlemen, let me see here. All right, our next question here. What is the typical insertion forces of the hyperboloid?
So I'll take that one again. Right. Pretty simple answer. The insertion forces range anywhere from 0.36 to 1.92 ounces per pin. The extraction is pretty close to that. It's 0.3 to 1.6 ounces per pin.
All right, thank you so much for that answer. All right, let me grab our next question here, gentlemen. All right, our next one here. Kevin, I'm going to jump over to you for this one. What are the current speeds of the hyperboloid contact, and are there any plans for future?
That's a good question. So currently, the KVPX connectors support up to 16 gigabits in differential speeds, 8 gigahertz for single-ended, and definitely the contact system is constantly in development and working towards higher speeds with sites on 32 gigabits and higher.
All right, thank you so much for that answer. All right, and we do have a couple questions just about the resources today, copy of the PowerPoint. If you guys look right in that resource list and scroll down, there is a copy of the PowerPoint that is in that resource widget. There's also a couple other items listed in there. So for all the attendees, if you want a copy of the slides or any of the resources from today, you can look right in that resource window and download anything at any time. So go ahead and do that at any time today. All right, let's move on to our next question here. All right, so this person is asking, are you seeing an increase in requests for fiber optic harsh environment connectors?
Yeah, so I'll answer this one, Katie. This is perfectly geared towards me. So I've come actually from recently in our SOCOM business unit, which is fiber optic and components. We just developed a backplane connector solution, which we term or brand name LightConnect. Actually, the editor on that standard is VITA 66.5. What it essentially is a backplane transceiver product and a backplane optical connector using an MT ferrule. We've done some very harsh environmental testing on the physical contact version with plans in the future to potentially move into some lens versions. We also we do a lot of work with essentially ARINC, and the expanded beam versions of simplex terminized, and connectorized solutions, and well, I guess various connectorized solutions, you could say. But as far as the backplane is concerned, and from our conversation today in VPX, please take a look at our Live Connect solution. That's currently our latest and greatest harsh environment backplane connector.
Okay, great. Thank you so much for that answer. All right, from all the attendees, if you do have a question today, go ahead and use that Q&A window and pop that question or comment in there and click submit. All right, gentlemen, our next one here. All right, this person is asking, how does breakage of one or basket strings affect usage, conductivity, mating force, debris, etc.? How often are broken strings seen?
Yeah,
Do you want to take that one?
so I'm looking for the question so I can read it again.
Yeah, sure. I can read it again for you, Kevin. How does breakage of one arm or basket string affect usage, conductivity, mating force, debris, etc.? How often are broken strings seen?
So that's a good question. I mean, it does occur. So during the assembly process, it's not uncommon for a wire to break as the contact is formed. We've done testing, with 2, 3, 4 wires, and as long as it's typically less than 2 wires, it doesn't affect the contact resistance to the point where you see contact failures or increased contact resistance. It's not desirable, but it does occur in the hyperboloid.
All right, great. Thank you so much, Kevin. And just a little follow-up to that. How are basket strings plated?
So it's a trying to think of the process is it's a wire plating. So I'm trying to think of the name of the process and I'm drawing a blank on it. But it's plated on a reel with wire. So, and then the wire is cut and formed into the contact off of that reel.
Okay, thank you so much, Kevin. And as mentioned, if we don't hear your answer today to a question, we will reach out to you following the webinar with your answer or even more information. All right, gentlemen, I'm just going to take a couple more today. This next one, I believe, Kevin, this one can go to you as well. What is the current carrying capabilities of the hyperboloid?
So in terms of KVPX, it uses our 0.4 millimeter hyperboloid. Each contact is rated up to 1.56 amps. So on the KVPX utility module, there are 3 power wafers. Each wafer has 2 bars in it that are connected to each other. And those 3 wafers combined can handle up to 37.5 amps. So,
all right, great. Thank you so much, Kevin. So, as I mentioned to the attendees, if you don't hear your question today, we will reach out to you. We're going to take about one more question. Any attendees that have any last-minute questions, go ahead and enter them now, and we'll reach out to you following today. So this last one, Kyle, I'm going to pass this one over to you. Is the KVPX aligned with any industry standard?
Yeah, thanks, Kitty. So KVPX ANSI Vita 63.0, which is titled Hyperboloid Alternative Connector for VPX, was written from our KVPX product. So it aligns with that standard, but the standard essentially provides an alternate connector to the Vita 46 VPX baseline standard connectors as well. So it aligns with both. because 46 and the 63 connectors are not intermatable, a Vita 63 plug-in module will not plug into a 46 and vice versa. However, their layouts are compatible, right? So the Vita 63 draft standard provides VPX users with the flexibility to choose a VPX module and backplane connector combination for their specific application requirements.
All right. Thank you so much, Kyle, for that last answer. So we are going to start to wrap the webinar up right now. So gentlemen, I want to say a huge thank you to both of you, to Kevin and Kyle, for a great presentation and for answering some of our attendees' questions. So gentlemen, thank you both so much.
Yeah, just thanks, Katie. I just wanted to mention there were a couple of questions in the list that we didn't get to, but please reach out to me either by LinkedIn or if you have further questions. I'm glad to take them, and I'm open to further conversations about the subject.
Take care, and we will speak with all of you soon.